So remember, a solenoid is what we call it when you wrap a whole bunch of wires in the same direction around an iron core, because each wire has its own magnetic field, so when they're all wrapped together, they tremendously amplify each other's magnetic fields. There's several variables. In our picture of a solenoid, we have the length of the solenoid. We have the number of turns of wire in the solenoid. We have the current. In fact, Ampere determined that the magnetic field inside a solenoid depended on certain variables. He found that a bigger current made a bigger magnetic field. He found that more turns of wire made a bigger magnetic field. If you start with 5 turns of wire, if you add 10 turns of wire, you've just doubled your magnetic field. If you start with 5 turns of wire and you make it 25 turns of wire, you just made the magnetic field 5 times stronger, which is really nice. That means we can customize the magnetic field, Emily, to any size that we want. He also found that it was dependent on the length of the solenoid, but the solenoid, the shorter it was, the smaller length was, the bigger the magnetic field. The more closely packed together the wires were, the bigger magnetic field. In other words, he said the magnetic field was proportional to that. Here is the equation. This is very, very similar to gravity was proportional to mm over r squared for gravitational field, and electric field was proportional to q over r squared. Pause the video for a second. So to turn this into an equation, you might recall that we had to add a constant. So to turn gravitational field into an equation, we had to put a big G there. And to turn electric field into an equation, we had to put a K there. So we're going to have to put a constant there too. Okay? What was big G? Who remembers? 6.67 times 10 to the 11, kind of a yucky one. K was a little nicer. It was 9 times 10 to the 9th. This is one of my favorite constants of all time. So the magnetic field, and remember the symbol for magnetic field is a capital B, and I'll put a subscript SOL for magnetic field in a solenoid. It's mu with a subscripted 0, which I always pronounce as mu naught, because I had a British high school physics teacher, and that is my homage. He never said 0. You counted naught, 1, 2, 3, 4, 5, 6, right? That's the British word for 0. So it's mu naught N times I over L, where N equals the number of turns of wire. How many loops of wire? You want to make the magnetic field twice as strong? Double the number of loops. I is the current in the wire, and L is the length of the solenoid. What's mu naught? It's on your formula sheet. Probably right where big G and little k are. What? Pi? What the heck does pi have to do with magnetic field strength? Well, the universe seems to like that number. It's 4 pi times 10 to the negative 7. It has one of the best names. It's called the permeability of free space. Connor, what did you learn in school today? Mummy, I learned that the permeability of free space is 4 pi times 10 to the negative 7. Oh, Connor, you are ever so clever. All of you today, every one of you must try entering this in your calculator in just a second, because about 80% of you are going to get an error. There's a software glitch, and we have to do a workaround. So please make sure you're following along today on your calculator. There's a second version of this equation that's often used in industry. Often in industry, instead of taking the total number of turns and dividing by, got another latecomer here, pause the video. as I was saying, there's a second version of this. This N is the number of turns of wire. This L is the length in meters. Sometimes they'll give that as a ratio as turns per meter. And so sometimes you'll see this. The magnetic field from a solenoid, here's a good sneeze, is equal to mu naught little n times I, where little n is the number of turns per meter. You'll know you're using this one because they don't give you a length in meters. I want you to realize how profound this is. Josh, this means if I'm a factory that makes solenoids, you can call me up and I can customize a magnetic field to any size that your industry application seems to want or warrant. I need a magnetic field of 0.63 Teslas. Okay, how long do you need the solenoid to be? How much space do you have for the solenoid? I got this much space. We can calculate how many turns of wire we need to fit in that much space. We can customize a magnetic field. Oh, and that's even removing the fact that we can also, with electronics, customize the current going through here. We can really pinpoint magnetic fields and make them as big or as small as we want. Okay. The Large Hadron Collider is basically a whole bunch of solenoids glued together in a large circle. It's more complicated than that, but it starts there. Let's do some. A solenoid is carrying a current of 4.2 amps. If the solenoid is 1.2 centimeters long and is made up of 750 turns of wire, what's the magnetic field at its center? Okay. Josh, what's this question asking me to find, my friend? Magnetic field. What's the symbol for magnetic field? And this is one, by the way, kids often want to write F. No, force is F. What's our symbol for magnetic field? So the first thing I'm going to say is B equals question mark. Josh, what's that 4.2? Oh, current, you say? What's that 1.2? And yeah, what is it? First of all, we're not going to use it. Better yet, let's cross out the 1.2 and above there, let's write 0.012 meters. Nice try, Mr. Dewick. That is the length of the solenoid. What's that 750? I know it says turns of wire, but in our solenoid equation for magnetic field, what variable is that going to be? Yep, capital N. How do I know this is the capital N one? Because they gave me a length. So, the magnetic field in a solenoid is mu naught N times I over L. What was mu naught? 4 pi times 10 to the negative 7. N is 750. I is 4.2.012. I need every single one of you. You must type this into your calculator because about 80% of you are going to get an error. You won't. I don't think the TIs give the error, but the Sharps and the Casios, I think, do. So once you've written that down, please try typing that in. Get an error? Okay. Who's getting the error? Raise your hand. Okay. Risa, yours worked? What kind of calculator do you have? Your Sharp worked? Okay. Who else has a Sharp that didn't work? Okay, so there's an issue with the software. By the way, the issue is your calculator doesn't like pi next to scientific notation. So what you're all going to have to do, you can write 4 pi times 10 to the negative 7, but all of you that got the error, here's what you're going to type. Type with me. You're going to go pi times 4 scientific notation. You got to switch the pi and the 4 around. Your calculator is happy having a number in front of scientific notation. Now, I would argue that pi is a number, and I don't know why it doesn't like that, but some software doesn't like that. And then times 750 times 4.2 divided by 0.012. So it's a pretty easy fix, but do you get 0.33 Teslas? Got an error still? Don't clear your calculator, please. Was it 0.33 Teslas? Okay. I would have no problem also on your test telling you the magnetic field and asking you how many coils of wire, how many turns of wire do we need. Get the N by itself, or get the I by itself, or get the L by itself. Mu naught is a constant, so I'm not going to have you get that by itself because it's always 4 pi times 10 to negative 7. But as always, I can reverse engineer this question, and you'll see a bunch like that in our homework. Number 8 says, find the field and the direction at the center of the coil. Let's do the field first. I notice they gave me 10 amps. And notice they gave me coils per meter. Connor K, did they tell me the length? So if you look at your formula sheet, you have two equations for magnetic field. We're going to use the one that doesn't have length in it. So it's going to be the mu naught. Can you keep reading to me? The one that doesn't have length in it, because they didn't give me a length. Yeah, the one that doesn't have an L in it. Yeah, it's Captain Obvious. What is it? Uppercase or lowercase n? Lowercase n times I, where this is the number of turns per meter. Okay. So this is going to have 4 pi times 10 to the negative 7. The number of turns per meter is 2,550. 10 amps. Let's see what we get. You get 0.032. We're not done. That's the magnitude. It also said find the direction. Now, looking at this picture, I guess we're looking down the center of the solenoid. We're looking down the center of the solenoid. What do you think those arrows are showing me? The current. So we imagine holding the solenoid in our hand. I guess I can only hold it this way or this way. I can't hold it this way because the solenoid is running into my page. We curl our fingers in the direction of the current. This way. What does my thumb tell me? So the North Pole would be, this is tricky to draw, right here out of the page. Oh, no. I have a symbol for a magnetic field out of the page. How would I show that? Yeah, so here, let's go. There. The magnetic field is coming out of the page. No, I'm not doing a happy face. We're doing physics. That should make you happy without a happy face. It's unnecessary. Physics itself is the happiness. If the current was going the other way, the North Pole would be into the page. So your factory, solenoid, your factory is called, we have 30 centimeters in which to install a solenoid. We're going to be winding it on a piece of cardboard, 30 centimeters long. How many turns of wire do we need to put around this if we want a magnetic field of 6.28 times 10 to negative 3 Teslas? And we're stuck with 5 amps. Again, the nice thing about a solenoid is it's a really customizable magnetic field, and 3 of the variables are easily customizable, so it gives us lots of flexibility. Pierce, what's this question asking me to find? What variable was how many turns of wire? Big, oh, thank you. See, Connor, that's how it's done. Big N. Could you look at the equation for the solenoid magnetic field and get the big N by itself? What N equals what over what, the whole thing. Read it to me. times L. Okay.
Divided by I. Divided by,
Mu naught.
and
The permeability of free space. Here, sure. Okay. We want a magnetic field of 6.28 times 10 to the negative 3. Devin, how many things are on the bottom of this fraction? I will need brackets around the bottom, right? L, 0.3. Nice try, Mr. Dewick. 4 pi times 10 to the negative 7. A few of your calculators that have the built-in constants might also have mu naught built in. I don't know. Times 5. How many turns? I think it's like 299.9 something, right? Clearly, I started with 300 turns of wire. And I think the unit for turns, Pierce, would be turns. I don't know. Okay. So, in addition to the homework from last day that I already assigned, you can now do number 5, number 6, number 7. You can skip number 9, or as I like to say, 9. 12. So I already said you can do 5, 6, 7. 12. And I'd already signed some questions last day. And can you now please get out the ultimate review that you can ignore, that I'm not going to be assessing you on because I've had to shorten things? Cross out number 1. Cross out number 2. I'm going to be emailing you a video tutorial tonight. It will talk about the cathode ray tube in the video tutorial. You can ignore that portion of things, but it'll be in there, I'm sure. But you can cross out number 2. I'm not going to put cathode ray on your test. I love number 3. We're doing a radius thing, so absolutely. Number 3, absolutely. You can cross out 4. 5 is good. Six is good. 7 is good. Cross out 8. 9 is good. 10 is good. Cross out 11. 12 is good. 13 is good. We already did 14. That was what explained the shrinking quarter that I showed you in the video last class. 15 is good. You can cross out 16. You can cross out 17. 18 is good. Apparently 19 is good, but it vanished. 20 is good. 21 is good. 22 is good. 23 is good. You can cross out 24. 25 is good. Number 25, it's asking you to find the magnetic force. And magnetic force on a wire is Bill. The key idea here is, which length do you use? Do you use this length, or this length, or that length? And the answer is, it's the length that's inside the magnetic field. You're going to use the 0.22. 26 is good. 27 is good. 28 is good. 29, 30 is good. But I crossed out 31. Cathode ray tube. I crossed out 32. I crossed out 33. I like 34. I like 34. Now, the only tricky part with number 34 is they're going to be using some electrostatics because they're giving you the voltage. So you're going to be using, from a couple of units ago, QV equals a half mv squared to find V, where you had the wings, and then B, find the radius. Scholarship questions I wouldn't worry about. Scholarship questions I wouldn't worry about. Look up. When current flows in this wire, the wire is forced upward. So when current goes this way, the wire is forced upward. Everybody point your right thumbs into my board. Current's kind of going this way. Wire's getting pushed upward. What direction is the magnetic field pointing? Yeah, right hand there, Pierce. I caught you. Which way is the magnetic field? Justin, get your right hand off your head and take part in this, please. So magnetic field is pointing this way. So that must mean that this is north and this is south. Right? Because magnetic field lines always point from? Okay. So here's the question. Suppose we bend the wire in a loop. What will happen? Well, along the left, we have the current going into the page, magnetic field that way. Right hand's up, come on. What's the left side of the wire going to feel? A force which way? Up. What about on the right side? Now the right side of the wire, the current's coming out of the page towards me because it's done a little loop. So point your thumbs out of the page. Magnetic field is still that way. The right side of the wire is going to feel a force which way? And this is going to spin, and we have just invented an electric motor. Oh, instead of a loop, make it a bunch of loops and hook it up to an axle, and now you've got a spinning motor. That's all an electric motor is. It's a very neat application of magnetic fields.